Okay, class. Let's have some understanding on how bond fades. Okay, so let's discuss some the nature of bond failure and understand how it is. How can you imagine the failure in terms of bond, considering two possibilities uh, on failure, which we are going to discuss here. Okay, so for plain bars, the failure is actually characterized by pull out. Okay, so pull out means the bar is actually uh, sliding or slipping through the inside of your surrounding concrete. And this may happen with or without the presence of splitting cracks. Okay, by the way, splitting cracks is just again a pattern of crack in which we can distinguish band failure with other types of cracks. Okay, so we have the shear crack, the flexural crack, the flexural shear crack, the web shear crack, and this time we have to understand what's the difference of those cracks with that of splitting cracks. So the other thing that we have to recognize on this nature of band failure is the the deformed bars. Okay, so when you're using a deformed bar, the failure is definitely by splitting. Okay, so it may also fail by pulling out of the concrete, but that is considered for very small bars. Okay, so like your diameter may be 10 or less. Okay, but for fairly larger bars like 12, 16, 20, etc., so the deformed bar fails on splitting. And of course, when the concrete has split, a secondary cracks may form. Okay, and this is what we don't want to happen. When secondary cracks forms, it complicates the situation. Okay. Okay, so let's look inside the deformed bar. So if you take a look closely on a deformed bar, the deformation of which is actually given to us by this figure here. When I pull this bar with a tension force of Tb, it's a single bar, I will expect that the concrete particles, especially those in the vicinity of this deformation, will actually resist, no? Okay, resist or give considerable resistance due to uh, the mechanical aggregate interlocking. Okay, so mechanically, physically, the particles will actually abut. Okay, and prevent this bar to move going to the right because it will produce what you call a wedging action. Parang pinipigil niya yun, no? A wedge is in Tagalog, it's a kalso, no? It is something that will prevent one to move uh, because there is something abutting it. Okay, pumipigil, no? Dun sa movement. And if the force TB is very big, the only way that this can move is when the concrete locally crush. Okay, so pag nadurog na yung konkreto dyan, dun na siya gagalaw. Or else, it will not move. No? It will not move if this has a very strong compressive strength. Okay, so uh, I'd like to focus more on how those splitting cracks happens. Okay, so if we take a look now on the inside of this reinforcing bar, okay, by visualizing it inside a hole, okay, if we have a hole here, we take note that when the concrete is pushing this reinforcement deformation here, this is a deformation, or there is uh, protrusions, okay, at certain parts of the reinforcement that allows the wedging action to be uh, mechanically possible, okay, and allowing a stronger, okay, mechanical action between the deformation and the concrete. So what will happen is that this steel bar will resist, okay, will resist this wedging action, or else uh, there will be movement, and that's what we don't want to happen. Okay, so this will now prevent, this will counter the wedging action. When you pull this at this point, exactly at this point, you have a bursting force, okay, that is normally very strong on the vertical direction, okay, because the weakness of the concrete will be on the normal direction of the force, not the tangential. Okay, so you see these forces now, which are in purple, are these forces here, and they are converted simply because this is circular into a radial force that will burst the concrete eventually if your TV is very big. Okay, so you call now this a bursting force on your concrete, and this bursting force will eventually give you a manifestation of splitting cracks. That's why you called it splitting cracks or splitting force, because the tendency for this concrete is to split, okay, into 2, 3, 4. Okay, so these are now your splitting cracks. Okay, so those are the splitting cracks. Okay, so that is what you can see now from the inside, and eventually it will be manifested on the outside of your reinforcement in this form. Okay, so you have now here some schematic illustrations of what splitting cracks are from the inside to the outside. Okay, so you can see now from the inside there's a crack, and then it will manifest eventually to the outside. Okay, so if the splitting cracks will, of course, must manifest or must originate from the reinforcement surface because of the deformation. So eventually you can see some cracks like this. And you call these corner cracks, obviously because they are the corners. You call these intermediate cracks because they are the intermediate bars. And you call these horizontal splitting cracks because they tend to split your beam horizontally into two components. Okay, and of course the problem here when there are splitting cracks, it can propagate longitudinally like this. Okay, so it can propagate longitudinally along the beam cross section, and the danger of propagation may cause the spalling off. Okay, it can be spalled off. Okay, it can fall. Okay, this can actually fall or spall off in one piece. Okay, and this also can spall in another piece. And when you talk of one piece, you can make the entirety of this longitudinal uh, view, okay, of this portion. So worst case scenario, this strip can fall from one beam end to the other. Okay, and these are the secondary cracks that we are referring to. Okay, the longitudinal cracks are actually the secondary cracks that we are uh, referring to. And basically, these are just schematic types of cracks that we may expect to happen when we are dealing with bond stress problems. And take note that in strength design concept, the bond stress not directly used because it does not provide adequate measures of safety against splitting bond failure. Okay? There are also a lack of correlation between the localized bar slippage from high flexural bond stress and the strength of a beam as represented by splitting and subsequent loss of anchorage at the tension bars. So ACI therefore uses the concept of anchorage band or development length. That is, at every section there must be adequate embedment in each direction as to develop the required strength of the steel bar. Okay, so we have some formula here that we normally see, and this is some historical equations that we can have to understand better the new equations today. Okay, so we recall that this is the basis of your flexural bond stress or the length of development. FYD we have 4UU. So for number 11 or 35 diameter bars and smaller, so UU is normally 9.5 square root of F prime CdV less than or equal to 800 psi. So therefore LD is simply plug in this value here, but this must be not be greater than 800 psi. So these are ACI, very old ACI equations. Now applying the factor of safety of 6/5 to avoid splitting failure before the band stress is distributed uniformly along its length. So this is what happens to the formula, okay? So this is just a factor of safety, okay, applied to the formula a while ago. And then some manipulations and some substitution on the area will give you this very basic. Okay, so ito na lang ang isipin mo na napakadali. 0.04 ABFY over square root of F prime C. Or if the limit of 800 psi is placed, it's simply 0.0004. Okay, you can approximate this as 0004 dBFY. Okay. Okay, we substitute AB to be pi dB squared over 4. Here, okay? So why is it that this is only dB? Because we directly substitute it on this 4UU FY dB, okay? With the 6 over 5 there. So, but these are old equations, class. But if you want to use this, you can use this still because they are the basic equations that are new equations today are derived from. Okay, so these are old ACI equations. But eventually in this lecture, I will be using the 31808 ACI because it's not different with this formula here, but it's more complete in terms of the factors or the parameters concerned. Okay, so in the equation 31808, two options may be used. The first one is using table 12.2.2, or this is the table, and or equation 12.2.3, which is simply a general equation. This is the one. Okay, so you can use this, you can use this. This is the simple equation, and this is the of course the detailed equation, just like shear and yes, just like shear, we have the simple and the detailed equation. Okay, take note of your psi t, psi e. In other lectures, I call it an alpha, beta, lambda. Okay, so we'll just use this because this is the one presented here. But in other books, you may be finding different notations on this. Okay. Okay. Unfortunately, I think I have to check first, class, and I'll tell you in the next video if this is good for both the English and the metric units. I think this is times 12. This is 4, 9 over 10. I think this is English units, class. Okay, so but I'll check on it. So if this is English or not, and I'll give you the alternate formula on the next video. Okay, so I'll cut my discussion here. I'll see you on the next video. Thank you.